Recently, Cbse has released a practice paper in physics. This is a good collection of the freshly prepared questions as well as the old style questions. Dear students, it does need your attention. You should solve this paper because some of the questions may surprise you. You need to read every single question very carefully. This question, number 12, the case study based question. In the sample paper, it was objective type. Now here it is a collection of the very short answer questions. The general instruction for you are read each question carefully, mark its parts and subpart of the question carefully. In this question, as you read, you will notice it has two parts, part A and part B, and each part has two subparts. Mark distribution should look like this. There are four parts and hence half mark for each. Let's attempt each part carefully. Answer part A. How many valence electrons will the impurity atom have in the outermost shell? You see, N-type semiconductor is produced by doping fifth group impurity atoms in the intrinsic semiconductor. Example of such elements are arsenic and antimony, as these belong to the fifth group as per the Mendeleev periodic table, and hence the number of electrons in its outermost shell should be 5. Thus, number of valence electrons in the outermost shell of impurity atoms should be 5. The second subpart of this question, what is the net charge on the semiconductor material after adding the impurity atoms? Now see, the idea is intrinsic semiconductor is neutral and the dopant atoms are also neutral, and hence the N-type semiconductor should also be neutral. Thus, net charge on the N-type semiconductor will be 0. N-type semiconductor should be neutral. Now part B. The purpose of the photodiode in reverse bias. Photodiodes are used in reverse bias because change in reverse saturation current is appreciable, and which happens to be the measure of intensity of incident radiation. Thus, photodiodes are used in reverse bias as change in reverse saturation current is appreciable, further it is also measure of intensity of incident radiation. Now the second subpart, the purpose of LED in forward bias. So when LED is used in forward bias, then large current flows due to diffusion of electrons, and it results in the production of monochromatic radiation. When LED is used in forward biased, then it results in large current due to diffusion of majority charge carriers, and hence in the production of monochromatic radiation. Hope you have read question number 2. It has 2 parts and there seems to be no subparts, and hence marks assigned should be 1 each. Now answer. Part A. The wavelength of de Broglie wave associated with electron of mass m and energy E is lambda E is equals to h upon 2me square root. This is relation number 1. Now the wavelength of de Broglie wave associated with photon of energy E is lambda of photon, that should be equals to hc by E, relation number 2. And according to the question, we are supposed to find the ratio of de Broglie wavelength associated with electron to that of the wavelength associated with the photon. Thus, lambda of electron upon lambda of photon, that should be equals to h upon 2me square root divided by hc by E. H and H will cancel, and this should be equals to, after simplification, 1 by C is square root of E by 2m. This is the required answer. Part B of the question is, why do macroscopic objects in our daily life not show wave-like properties, whereas in the subatomic domain, the wave-like character is significant? Answer to this question is, for the macroscopic objects in our day-to-day life, the wavelength of de Broglie wave is negligible compared to the size of the object, and hence these are not visible. However, in subatomic domain, the wavelength of the de Broglie waves is comparable to the size of the subatomic particles, and hence these are significant. Now answer to part B of the question. In day-to-day life, the wavelength of the de Broglie wave associated with the macroscopic objects is extremely tiny compared to the size of the macroscopic objects. And hence, de Broglie waves are not visible in day-to-day life. However, for the subatomic particles, the wavelength of the de Broglie waves is significantly large compared to size of the subatomic particle. and hence wave nature dominates over the particle nature. It is the OR part of the second question. It has two parts, part A and part B. And by the construct of the question, it appears that part A is for half marks and part B is for 1.5 marks. Answer, part A. The transition Ni is equals to 2 to Nf is equals to 3 will give absorption spectra. It is due to the fact that the electron in the lower orbit absorbs energy and jumps to the higher orbit. Part B, the transition Ni is equals to 3 to Nf is equals to 1 will give Lyman spectral line. You should be able to recall that the Lyman spectral series is obtained corresponding to the transition from any higher orbit to n is equals to 1. The transition Ni is equals to 4 to Nf is equals to 2 will give Balmer spectral line. You should be able to recall that Balmer spectral series is obtained corresponding to transition from any higher orbit to the lower orbit n is equals to 2. The transition Ni is equals to 4 to Nf is equals to 2 will give Paschen spectral line, not the bracket spectral line as mentioned. This question 3 has two parts, part A and part B. To me, marks distribution appears to be half marks for this subpart and half mark for this subpart and 1 mark for this part B of the question. Now answer, part A. Barrier potential is the potential difference across the PN junction of a PN diode. In this diagram, it is represented by VB. The next part of the question is, what is impact on the barrier potential when PN junction is connected in forward bias? Of course, net potential difference across the junction decreases as the direction of electric field caused by the external battery is opposite to the direction of the electric field within the PN junction. In forward bias, net potential across the decreases in forward bias. Quick explanation. Here is the PN diode. This happens to be the junction and the depletion layer across it. This is P side, this is N side. When it is forward biased, positive terminal is connected to P side and negative terminal to N side. Due to this external battery, direction of electric field is from P to N. However, electric field within the PN junction, this is from N to P. And that is why net potential difference across the junction got to be V minus VB modulus. As V increases, this value decreases. Now next part of the question, how does current changes as voltage applied across the PN junction varies from a small to very high in reverse bias condition? When reverse bias potential difference is gradually increased, then current due to drift of minority charge carriers increases, and then becomes constant, which is called as reverse saturation current. When the value of applied potential difference becomes equals to Zener potential, current increases abruptly. And this happens to be the graph in reverse bias. This is potential difference and this is current. Current in reverse bias is of the order of microampere. As I told you, current first increases very slowly, then becomes constant, and this constant current is termed as the reverse saturation current for a particular value of applied voltage V equals to Vz. This current abruptly increases to very high value. Hope you have read question number 4. It has two parts, part A and part B. For me, part A is for 2 marks. However, 2 subparts of part B, they are for marks half each. Let us proceed for the solution of part A. For total internal reflection at point P, let's assume this point to be P. Angle of incidence, which happens to be 45 degree, should be greater than the critical angle. Take sine on both the sides, that is sine 45 degree is greater than sine of C. Further, on the left hand side, sine 45 degree is 1 by root 2. This should be greater than sine C, by definition is 1 by mu, and this implies that mu should be greater than root 2. So the minimum value of the refractive index should be equals to root 2. Now answer B, subpart first. When the prism in vacuum, then n is equals to sine A plus delta m by 2 upon sine A by 2. Here A is the prism angle and delta m happens to be minimum angle of deviation. This formula suggests for the larger value of delta m, mu should also be larger. When the same prism is dipped in a liquid of refractive index n dash less than n, then this formula changes to n by n dash equals to sine A plus delta m by 2 upon sine A by 2. This is relation number 2. As n by n dash is less than n, so we expect that delta m dash should be less than delta m. This is delta m dash. Second, the subpart. Now answer to second subpart. In this question is given that incident blue light undergoes TIR. However, red incident light for the same angle of incidence on the second surface of the prism does not undergo TIR. And then what is the reason for it? For TIR to occur, angle of incidence should be greater than critical angle, but critical angle for the red color is greater than the critical angle of the blue color. Hint, sin C is equals to 1 by mu. So red color will not undergo total internal reflection. This is all part of fourth question. It has three subparts: part A, part B, and part C. It seems that each part is for 1 mark. Hope you have read this question. We are supposed to copy the diagram and complete the ray diagram to represent an image as viewed from the left side, means from this side. And we are also supposed to tell the image will be real or virtual. So let us try it. Answer, part A. I have copied the diagram. Now let's complete the ray diagram. To complete the ray diagram, I need to draw a tangent at point A. Thus, normal at point A should pass through C. Next part, this ray OA is traveling from denser to rarer medium, and hence we expect that it should deviate away from the normal. Thus, AB is a refracted ray. Now next, you extend this AB ray in backward direction. Had there been no change in the medium at this point D, then this ray AB should have appeared to come from this point I dash. I dash should represent the final image, which is virtual in nature. Now answer to part B. Magnification before interchange. M equals to minus FO by FE, as FO is much greater than FE, so M is also much greater than 1. Magnification after magnification, after interchange of lenses. M equals to minus Fe by Fo. Here M should be extremely small compared to 1, and hence image will be highly diminished and will have low intensity. Here M dash is very small compared to 1, and hence image will be highly diminished and of low intensity. Answer part C. Larger aperture of objective lens in the telescopes in fact ensures the brightness of the image. Now to question number 5. It has 3 parts, A, B and C. It appears that each part is for 1 marks. Now answer part A. Hope you have read this question. Energy of electron in the nth allowed orbit En equals to minus 13.6 upon n square electron volt. It implies that E1 equals to minus 13.6 by 1 square equals to minus 13.6 electron volt. E2 equals to minus 13.6 divided by 2 square and equals to minus 3.4 electron volt. E3 equals to minus 13.6 by 3 square equals to minus 1.51 electron volt. Similarly, E infinity, that should be equals to minus 13.6 upon infinity square, and this is equals to 0 electron volt. Minimum energy will be radiated corresponding to the transition from n is equals to 2 to n is equals to 1. Minimum energy will be released or radiated corresponding to N2 is equals to 2 to N1 is equals to 1. Thus, delta E min, that will be equals to E2 minus E1 equals to minus 3.4 minus 13.6 equals to plus 10.2 electron volt. Maximum energy will be radiated corresponding to the transition from n is equals to infinity to n is equals to 1. Thus, delta E max equals to E infinity minus E1, and this is equals to 0 minus 13.6, and this is equals to plus 13.6 electron volt. Now, delta E min to delta E max equals to 10.2 electron volt upon 13.6 electron volt. These two numbers are multiple of 3.4, 3.43 za, 3.4 za, and this is equals to 0.75. Answer part B. According to de Broglie explanation of Bohr's quantization condition of an orbiting electron, two pi Rn is equals to n times h by 2 pi. For second allowed orbit, 2 pi R2 is equals to 2 multiplied by h by 2 pi. Particle wave in n is equals to 2 should look like this. This happens to be n is equals to 2, second allowed orbit. This is the nucleus. For third allowed orbit, two pi R3 equals to 3 multiplied by h by 2 pi. And the wave picture should look like this. Here is the third allowed orbit. Now answer part C. De Broglie wavelength of electron in the second allowed orbit should be given by now according to the Bohr's angular momentum postulate, from relation to mv2 is equals to h by pi r2. Put it in 1. Lambda is equals to h upon h by pi r2. This is equals to pi r2. 4 pi r1 as r2 is equals to 4 r1. Note Rn is equals to n square times r1. So this will be the required value of the wavelength in the second allowed orbit of the hydrogen atom. Question number 6. It has two parts, part A and part B. I would like to assign 1 mark for part A and 2 marks for part B. Answer part A. For the positive half cycle, terminal A is positive and terminal B is negative, and this will ensure that the diode D1 is forward bias and diode D2 is reverse bias because of the obvious reasons. For the negative half cycle, terminal A is negative and terminal B is positive. And this will ensure that D1 becomes reverse biased and D2 forward biased. Now answer part B. If we look at the circuit diagram, we can easily guess that terminal A is at a higher potential while terminal C is at a lower potential. This will ensure that diode D2 is reverse biased and current will not flow through it. Diode D1 is forward biased and current does flow through it. The direction of current from the battery is I. It will not divide at terminal A because diode D2 is reverse biased, and hence same current I should flow through diode D1. Current over here is I. It continues to flow. It will not redistribute at point C because diode D2 is reverse biased. So same current passes through this 70 ohm resistor and enters the negative terminal. This completes the current distribution. Current flowing through the diode should be given by I equals to, now you see, this current I flows through resistance 30 ohm of diode D1, then through 100 ohm resistor, then through 50 ohm resistor, and hence I should be given by 5 divided by 30 plus 100 plus 70 amperes. This is equals to 5 by 200 amperes, and this is further equals to 25 milliampere. Now see, current flowing through diode D1 is 25 milliampere, which is less than 30 milliampere. So we expect diode D1 to be safe as current flows. And similarly, diode D2 got to be safe as current is not flowing through it. And hence, in this arrangement, both the diodes are safe.